Good morning, students. Myself, Vijay Shankar from EC Department, Central Engineering College. Today, we are going to discuss about the properties of Fourier transform. That is the second part of the second unit. The Fourier transform. What is the definition of Fourier transform and the introduction of the Fourier transform we seen in the last class. Now we go for the properties of Fourier transform. In yesterday's class, I already explained about what are the same properties are there in the Fourier series and the Fourier transform. Fourier series and the Fourier transform. The linearity, time shift, the frequency shift, time differentiation, scaling property, convolution in time, modulation in time, Parseval's theorem, and symmetry properties. The additional three more properties are there in the Fourier transformation. That is frequency differentiation. Another one is a duality property and the integration property. These are the three more another properties are there in the Fourier transformation. So the first property we can see the linearity property. Linearity property. The linearity, if x of t, the statement saying that if x of t Fourier transformation x of omega, Fourier transformation x of omega, and y of t, the Fourier transformation of y of omega, that z of t is equal to a into x of t plus b into y of t. You can prove that it is a into x of omega plus b into y of omega. So I got the definition of the Fourier transformation. Then Fourier transformation x of omega is equal to integral minus infinite to infinite x of t into e power minus j omega t, e power minus j omega t dt. In the statement saying that we can take the z of t as e into x of t, b into y of t. So instead of x, I take it as a z. So let us take it as a z of omega is equal to integral minus infinite to infinite. Z of t you can take as e into x of t plus b into y of t will multiply with e power minus j omega dt. Got it, my students? So expand this or the split the two parts as e into integral minus infinite to infinite x of t e power minus j omega t dt as one part plus b into integral minus infinite to infinite of y of t e power minus j omega t dt. So this is also the one of the definition of the Fourier transformation only, not the one of it, the Fourier transformation definition with the signal x of. So a into x of omega plus b into, this is also the definition of the Fourier transformation with the signal of y of t. So the frequency is y of omega. So z of omega is equal to a into x of omega plus b into y of omega. Got it, my students? Z of omega is equal to a into x of omega plus b into y of. This is both the Fourier series and the Fourier transformation. The proof of the linearity is the same, but the definition is a different. There it is x of k is equal to integral minus infinite to infinite x of t into e power minus j k omega naught t dt. That integration is not the minus. You can take the minus infinite to infinite, or it is a t integration with 1 by t, because the Fourier series is for the periodic signals and Fourier transformation is for the non-periodic signals also. And the second one, the time shift property. The time is shifted with the t0 samples. The same thing, the exponential, the negative exponential value is multiplied by the frequency function x of omega with the t as a t naught. Let me take the time is shifted with the t minus t naught. Time is shifted with the t minus t naught. Let's if I am taking the z of omega is equal to integral minus infinite to infinite. Z of t, now I am taking that is x of minus t minus naught into e power minus j omega t only into d. So assume on the left, we can take t minus t naught is equal to m. T minus t naught is equal to m, and the t is equal to m plus t naught. Where the t naught is a constant, apply the derivative on both sides. Dt is equal to dm plus 0. That is equal to integral minus infinite to infinite x of m into e power minus j omega into t as the m plus t naught. M plus t naught, and the dt now it is becomes of dm. And you can write the two parts of the exponential as x of m into e power minus j omega m dm, and into the e power minus j omega into t naught. So observe here, there is a definition of the Fourier transformation with the variable of m, the x function. So e power minus finally the z of omega is equal to the function as x of omega into e power minus j omega t naught. See, when the time is shifted with the t naught sample, so the frequency x of omega is multiplied with the negative exponential with the t naught as the power. Z of omega is equal to x of omega into e power minus j omega t naught. The time shift property, e power minus j omega t naught into y of omega. They take is a y of omega as a frequency, the y of t signal. Coming to the frequency shift also. The previously the time is shifted with the t naught samples. There is a multiplication factor for the frequency domain x of omega, the e power minus j omega into t naught. So the frequency shifted with the beta samples. The time domain x of t signal is multiplied with a positive exponential with the b value instead of omega, that is a beta. Okay, now let us see that also. Let I am taking the z of omega is equal to integral minus infinite to infinite. The z of t can take as z of t as e power j beta into t x of t. There is a signal we can take, and through that there is a shift in the frequency. Power minus j omega td. That is equal to. So integral minus infinite to infinite. X of t is a signal, and here the both are base of the same e power. Take the minus as a common, and the t is also the common. The first j, let us take the j is also common, minus j omega, and it is a minus beta into t dt. So see the e power minus j omega t and e power minus into minus is a plus e power j beta. So observe this equation is the same as the definition of the Fourier transform only, but instead of omega, it is a omega minus beta. So the frequency is x of omega minus the beta. The x of t is the Fourier transformation of x of omega. Thus x of t is multiplied with the positive exponential e power beta into t. There is a shift occurs in the frequency with the beta samples. Got it, my students? If they take it, it states that the shifting in the frequency by beta in frequency domain is equivalent to the multiplying the time domain signal by e power j beta into t. So x of omega minus beta, the frequency shift. Is also the similar concept of the Fourier series as usual, but there is a e power j k naught into omega t. So the scaling in the Fourier series, the time scaling the xa of t, the Fourier series, the time scaling of xa of t, the Fourier transformation is x of omega, because the time is the x of t, the time period is a t. For x of t, the time period is a t. The xa of t, the time period is a t by. The time period is a t by. And for the x of t, the frequency is omega naught. The frequency is omega naught. And for xa of t, the frequency is a into omega naught, because it's a periodic signals. The time is decreases means the frequency is increases. If the frequency is decreases, the time is decreases. So for that case, the xa of t, the scaling of the Fourier series, we got the x of omega. But the Fourier transformation, it is not for the periodics, it is only for non-periodic signals also. So the xa of t, the Fourier transformation, we got that 1 by a into x of omega by a. 1 by a, or 1 by the magnitude of a into x of omega by a. So the compression of a signal in the time domain xa of t, the compression of a signal in time domain is equivalent to the expansion in the frequency domain and vice versa. If suppose the xa of t, there is a compression, we can observe that xa of xt by a is expansion, is a compression and is a expansion. The signal time domain is a compression, the frequency is expansion. Expansion is by a, will get here, omega by a, and the time is multiplied, the frequency is divided by with the same scaling. Now, you can use the Fourier transformation definition to prove the scaling property, the integral minus infinite to infinite. Instead of z of t, I am taking here as a xa of t into e power minus j omega dt. Is a formula for the z transformation, not the z, the Fourier transformation, sorry. The z is a variable I am taking here. The z of t, actually the z of omega is equal to the Fourier transformation in terms of the z minus infinite to infinite, z of t e power minus j omega dt. So z of t as taking as a x of a into t as a scaling factor, or we can say it is a compression in the time signal. Compression in the time signal. So let us assume that the at is equal to m and the t is equal to m by a, and apply the derivative on both sides. So dt is equal to 1 by a into dm. Okay, substitute here the integral minus infinite to infinite, x of at is a m e power minus j omega into the t. Now it becomes of 1 by a, and dt is 1 by a into dm. Okay. Now the 1 by a is a constant, my dear students. You can write it as a 1 by a, it's the magnitude. If it is minus infinite to infinite, x of m e power, rewrite this function e power j omega by a into m into dm. Okay. Observe this equation is one of the the definition of the Fourier transform with the variable of m here instead of omega, that is a omega by a. If it is a omega, it will get the x of omega. If it is a omega by a, the x of omega by a. So 1 by the magnitude of a into x of omega by a. Z of omega is equal. Okay. The scaling Compression in the time domain means there is a expansion in the frequency domain and vice versa. The fourth property, the time scaling property. Fourth property, the time scaling property. Next one, fifth property, frequency differentiation. The frequency differentiation property is not there in the Fourier series. We have only the time differentiation. So time differentiation, before the seeing the frequency differentiation, first of all, you can see the time differentiation. What is the meaning? Differentiation in time domain corresponds to the multiplying by j omega in the frequency domain. It attenuates high frequency components of the signal. Time differentiation. That we know the definition of the inverse Fourier transformation. Inverse Fourier transformation definition is x of t is equal to 1 by 2 pi integral minus infinite to infinite. The frequency domain is the input now, x of omega. Exponential is a positive exponential, e power j omega t, and integral is with respect to the omega. Is a formula for, or it is a definition of the inverse Fourier transformation. Now apply the derivative on both sides. Here in this also the x of t is the Fourier transformation pair of x of omega. The Fourier transformation pair of x of omega. X of t, the Fourier transformation x of omega. X of omega is inverse Fourier transformation is x of. Okay, apply the derivative on both sides. D by dt of x of t. D by dt of x of t means we're applying the derivative with respect to the time. So in this, the right hand side expression having only the time is in the exponential. 1 by 2 pi, the integral minus infinite to infinite x of omega into d omega is a constant. Now apply the e power j omega t, e power j omega t into, because we are applying the derivative, so into the t coefficient. What is the t coefficient? J omega is equal to, write the j omega in the outside, j omega into 1 by the 2 pi integral minus, or otherwise you can write this as 1 by 2 pi integral minus infinite to infinite j omega into x of omega. J omega into x of omega. Into e power j omega t and the d omega. What it matters for? So it is a d by dt of x of. So in this inverse Fourier transformation formula, the x of t is a Fourier transformation pair of x of omega. This is also the same expression, but instead of x of t, it is applied the derivative. When we apply the derivative for the time domain function, there is a multiplication factor j omega for the frequency. So these two are also the Fourier transformation pairs. D by dt of x of t is a Fourier transformation pair of j omega into x of omega. Okay. So d by dt can apply the x of omega, d by dt for j omega t and j omega x of omega is a Fourier transformation base derivative of input signal x of t with respect to the time. After applying the Fourier transformation, we get j omega is multiplication factor of the frequency domain x of omega. Okay. The same as in the Fourier series also. Now we can see the frequency differentiation. Frequency differentiation. Previously, we apply the derivative for the time domain. Now we can apply the derivative to the frequency. To prove this, You take the definition of the Fourier transformation, the integral minus infinite to infinite x of t e power minus j omega t dt. So d by d omega into x of omega is equal to, I'm applying the derivative with respect to the omega, so minus infinite to infinite, the integral x of t. Here the derivative to further respect to the omega minus j omega t, and the coefficient of omega is a minus jd, minus j into td. So that is equal to integral minus infinite to infinite minus j into t x of t minus j into t x of t e power minus j omega t dt is equal to. Now again you can observe here, these two are the definition of the Fourier transformation with the pairs of d by d omega into x of omega is a Fourier transformation pair of minus jt into x of t or minus j into t x of t is a Fourier transformation of d by d omega of j omega, or the d by d of j omega x of omega. Sorry, what it matters to us. So d by d omega, you get the minus gt into this function is x of omega 1. But you don't write like this is x of omega and minus gt into x of t is a pair of d by d omega of x of omega. Okay. So this is a frequency differentiation property is not there in the Fourier series. Okay, my dear students. Now you can go for the another property, the convolution property. Convolution property. So convolution property, the convolution in time domain, there is a product in the frequency domain. Let's say here, I will explain in the whiteboard. Convolution in time domain, convolution. In time domain. So what is a z of t? You can take as x of t with the convolution of y of t. Apply the Fourier transformation. We'll get z of omega is equal to the frequency domain function is a product x of omega into y of omega. So time is convolution, the frequency is a product. Let us take the proof. So z of omega is equal to the formula of Fourier transformation. I directly am substituting the z of t as x of t with the convolution of y of t into e power minus j omega t dt. So definition of the Fourier transformation. And we already know the integral x of t, the convolution of y of t is the integral of minus infinite to infinite this one. For these also we'll get the integral of minus infinite to infinite x of tau y of t minus tau d tau. Is a formula for the convolution of two fast signals e power minus j omega t d. and rewrite this equation. The tau is in one integral minus infinite to infinite x of tau d tau, and the t terms in the another integral. The integral minus infinite to infinite of y of t minus tau e power minus j omega t d. By using the time shift property, the frequency is the integral minus infinite to infinite x of tau d tau. I'm directly substituting here without taking t minus tau is equal to m and the t is equal to m plus tau like that. By using the second property, the time shift property of the Fourier transformation, the frequency domain, the y of omega, is multiplied with the e power, with the factor of here the tau is there, minus j omega tau. The tau samples are shifted towards the right side. The time shifting is multiplied with the frequency domain, the y of omega. So again, you can see here in the right hand side, the integral minus infinite to infinite, left hand side, the x of tau e power minus j omega tau d tau into y of omega. See, this is also one of the definition of the Fourier transformation. Only instead of t, the dummy variable is the tau. So x of omega. So x of omega into y of omega. Therefore, the Fourier transformation z of omega is equal to, we got the x of omega into y of omega. Got it, Madam? This is a convolution in time domain. The frequency is a product. Okay. So convolution. The next eighth property is an integration property. So the integration property is not there in the Fourier series. We have only in the Fourier transformation only. So what is the meaning of the integration? The integration time represents a smoothing in the time domain. This smoothing in the time domain corresponds de-emphasizing the high frequency component of the signal. So how we can do this? Let us take the integral minus infinite to t x of tau d tau. We can prove that 1 by j omega into x of omega. So the differentiation, see, time is different d by dt of x of t. So what is the Fourier transformation we got? Fourier transformation is j omega is multiplied x of omega. When we apply the integral in the time domain, the minus infinite to t x of tau d tau, its Fourier transformation is integration x of omega by the j omega. The j omega is divided for the frequency here. When we apply the integration for the time and we apply the derivative for the time, the multiplication factor for the frequency domain is j omega. Okay. Now see, if I am taking the x of t is equal to x of t, x of t is equal to x of t. Okay. When the t is equal to tau, t is equal to tau. The tau is also the time period. So I am changing this x of one of the x of t here, x of tau, x of tau, and that is equal to integral d by dt. If I am using the d by dt here, derivative of integral will get the same thing on. Derivative of integral will get the same thing. So, and the limitations also, they are asking that take the limitations as 0 to t, not the 0 to t, minus infinite to t. So x of tau, and actually we are applying the derivative with respect to the t means the dt only. The t is tau here, taking the tau here, d by dt of integral minus t to the t, x of tau, the d tau. Okay. First of all, I take the x of t is equal to x of t and the t is equal to tau. I replace the t as a tau and without changing this previous expression, I applied derivative and integral. Derivative and integral means the same signal only will get the x of t, x of tau. Okay. Here it is x of t is equal to, now we got the d by dt of the integral minus infinity to the t x of tau beta. Apply the Fourier transformation on both sides. Apply the Fourier transformation on both sides. The Fourier transform of x of t, Fourier transform of x of t is equal to the Fourier transform of d by dt of the integral minus infinity to t x of tau beta. Okay. Got it, my dear students? Now, it is a Fourier transformation of x of t. What is the x of t? The Fourier transformation is x of omega. So, in the left hand side, it is x of omega is equal to, what is the Fourier transformation of derivative of any signal? Derivative, now like told that derivative is d by dt of x of t. D by dt of x of t. Instead of x of t, here it is an integral function totally. Is j omega into x of omega. J omega into x of omega. Any Fourier transformation is x of omega only. So now I am taking the Fourier transformation of this function as j omega into, I am not taking here the directly, that is x of omega, j omega into the Fourier transformation of x of t. Okay, the Fourier transformation of x of t, nothing but x of omega. So here also I am taking the j omega into the Fourier transformation of integral minus infinity to the t x of tau beta. Got it, my students? As of the same here. So cross multiply here the x of omega by the j omega is equal to, it's a Fourier transform of integral minus infinity to the t x of tau beta. Okay. Therefore, is a Fourier transformation pair. So integral minus infinite to infinite, or the infinite of t, the x of tau d tau is a Fourier transformation pair of x of omega by the j omega. Got it, my students? So the Fourier transformation of integral minus infinity to the x of tau d tau is equal to, we are writing because it's here the Fourier transformation of. So if I am removing this Fourier transformation of and write this only the signal, the integral minus infinity x of tau d tau, and is a pair, the Fourier transformation pair of x of omega by j omega. Got it, my students? The integration property. Coming to the ninth property, the modulation property. We already seen this modulation property in the Fourier series also. Modulation means is a multiplication time domain. So time is multiplied, frequency is convolution. If time is convolution, the frequency is product or nothing but multiplication. Okay. Now, we'll explain this in the whiteboard. See, the statement is saying that z of t is x of t, y of t, 1 by 2 pi x of omega with the convolution of y of omega. With the convolution of y of omega. Modulation property. Let us see. Modulation property. Statement saying that it is a z of t is equal to multiplying of the two signals x of t and y of t. The Fourier transformation is z of omega is equal to 1 by 2 pi multiplied with the convolution of the two functions x of omega into y of omega. X of omega into y of omega. It's a proof. Now I'm taking the z of omega, the definition of the Fourier transformation. Z of omega is equal to integral minus infinite to infinite. Directly I'm writing the z of t, x of t into y of t, e power minus j omega t dt. J omega t dt. So in this, the x of t, according to the inverse Fourier transformation formula, the x of t is equal to 1 by 2 pi integral minus infinite to infinite x of omega into e power plus j omega t into d. For our convenience, if I take the e power j omega and e power minus j omega, it becomes of e power 0, that is the value is 1. You can't prove the modulation property or the multiplication property to get this a convolution in the frequency. So change is the t as x of lambda is equal to 1 by 2 pi integral minus infinite to infinite x of omega into e power j omega into lambda into d lambda. Means t is changes to the lambda value for our convenience only. So z of omega is equal to, replace the x of t here, integral minus infinite to infinite, 1 by 2 pi integral minus infinite to infinite x of omega into e power j omega lambda into d lambda. Other function is y of t e power minus j omega t dt. What it matters is x of t I substitute as an inverse Fourier transformation. So rewrite this equation as a 1 by 2 pi, you can write outside, integral minus infinite to infinite x of omega and another integral minus infinite to infinite y of t e power minus j is take the common, and it is not, my dear students, the fees can change this value as here itself the t only. Omega you can change as a lambda. Omega you can change as a lambda. It is also the t. It is also the t, and omega you can change as a lambda. Okay. Omega is a lambda, and this is also the lambda value. And this value is a t, and it is also the dt of. Because it is inverse Fourier transformation, this is also the lambda, here also it is a lambda one. Okay, I will check this. So x of lambda e power j lambda into t, and here it is not the dt, my dear students. This is also d omega lambda, and here also it is not the dt. d omega. So in this, I change the omega as replace omega as lambda. Okay. So omega lambda and e power j lambda into t d omega is a d lambda. So here also you get the lambda and here also the lambda and it is a d lambda. Okay. Now this is not the omega, it's lambda and you can write this d lambda here, d lambda. Now what is a common term here? E power j omega and here take the minus lambda into t. See the two functions of the exponential is e power minus j omega t and e power plus j lambda into t dt. Okay. So according to the third property, here they're saying that y of t e power minus j omega minus omega minus lambda into t is a frequency shift property 1 by 2 pi into the integral minus infinite to infinite x of tau d tau x of tau d tau by using the frequency shift property. This total function we can write as y of omega minus lambda. Now the expression is 1 by 2 pi integral minus infinite to infinite x of tau y of omega minus tau d tau. So it is the same as x of tau, x of lambda, y of omega minus lambda d lambda is as of a convolution formula, the x of t, the convolution of y of t is a capital letters, my students. Y is the convolution formula is a minus infinite to infinite x of tau y of t minus tau d tau. See the same formula, instead of tau here the lambda is there and instead of t here the omega minus tau is a lambda and d lambda is y of t. Actually y of t is equal to the t. Now here the omega, so the left hand side it becomes of y 1 by 2 pi into 1 by 2 pi into the omega is there, the t means x of t with the convolution of y of t. So with the omega instead of t, so x of omega with the convolution of y of omega. Got it? Means the input is multiplied with the multiple modulation. The frequency, the time is multiplied, the frequency is a convolution 1 by 2 pi into x of omega with the convolution of y of omega. Okay, my dear students. We got the 1 by 2 pi. So the x of t 1 by 2 pi, the integral minus infinite to infinite x of tau e power j tau into t d tau. Replace this function and simplify, you get the x of omega with the convolution of y of omega. So next is the duality property and symmetry property and the Parseval's theorem also.